It's TED Talks Daily. I'm Elise Hu, and I just spent the last few days at our TED Monterey 2021 conference, where engineer Kathryn A. Whitehead unpacked just how cool the science is behind mRNA. mRNA made vaccines against coronavirus possible. In her talk from the TED stage, she explains what was so tricky about getting mRNA into our cells, which makes the fact that it's working in our bodies that much more awesome.
Hey, this is Adam Grant of Taken for Granted. This year, we worked with our sponsor Hilton to explore insights from their award-winning workplace. Stay tuned for a story from Macarena, a manager in hotel operations, who's learning the best way to employ radical candor in a culture built on hospitality.
What if I told you that the pandemic will save the lives of millions of people? It's a difficult thing to consider, given how many loved ones we've already lost. But throughout the course of human history, massive public health crises have resulted in innovation in healthcare and technology. For example, the Black Death gave rise to the Gutenberg Press, and the 1918 flu pandemic led to modern vaccine technology. The COVID-19 pandemic has and will be no different. Just look at our vaccines, normally developed over many years, and the mRNA vaccines were deployed in a mind-blowing 11 months. How is that even possible? It was possible because scientists have been working for many years to get us to the point where we could use mRNA quickly in an emergency situation. Specifically, we've been working on how to help mRNA with its biggest problem, which is that it doesn't normally go to the right places inside of our bodies. Fortunately, we got around that problem just in time, and I'd like to tell you about the technology that we use to do it. When mRNA is administered, it's injected into our muscles or our bloodstream, but we actually need it to go inside of our cells. Unfortunately, mRNA is fragile, and our bodies will destroy it before it goes very far. You can think of mRNA like a glass vase that you'd like to send in the mail. Without a box and bubble wrap, it'll break long before it's been delivered. And without an address on the box, your postal delivery service will have no idea where to take it. And so, if we're going to use mRNA as a therapeutic, it needs our help. It needs protection, and it needs to be told where to go. And that's where I come in. For over 5 decades, scientists and engineers like myself have been creating the shipping materials for nucleic acid drugs like DNA and RNA. Through trial and error, we've created packages that deliver intact bases to the wrong address, that deliver to the right address, but with a broken base, packages that get ripped apart by attacking dogs, and packages that throw out the mail carrier's back. It's taken many years to get the science right. Let me tell you the result. These tiny balls of fat that we call lipid nanoparticles. Let me tell you what they are and how they work. So first of all, nano just means really, really small. Think of how small a person is compared to the diameter of the Earth. That's how small a nanoparticle is compared to the person. These nanoparticles are made up of several fatty molecules called lipids. Fat is an awesome packing material, nice and bouncy. Interestingly, our cells are also surrounded by fat to keep them flexible and protected. Years ago, scientists had the idea to create lipid nanoparticles that would act like a Trojan horse. Because the lipids in the nanoparticle look similar to the membranes that surround our cells, the cells are willing to bring the nanoparticle inside, and that's when the mRNA is released into the cell. So what exactly are the lipids in these nanoparticles? There are 4 ingredients in addition to the mRNA, and I'll tell you about each one. First, there's a lipid called a phospholipid. This is the primary ingredient in our cell membranes, which are the walls of fat that separate the insides of our cells from everything that surrounds them. Phospholipids have a head that likes water and a tail that likes other fatty things. So when you throw a bunch of phospholipids together in water, they form this beautiful structure called a lipid bilayer. In lipid nanoparticles, phospholipids have a similar role of keeping all of the other ingredients organized. Second, there's a lipid called cholesterol. Why, if cholesterol has a bad reputation, would we want to use it in a therapeutic nanoparticle? It turns out that while cholesterol can be bad when it's in our bloodstream, it's actually a really good thing for our cell membranes. And that's because those phospholipids I just told you about, they are entirely too free with themselves, and they are prone to falling apart. Cholesterol is a stiff molecule that wedges itself in between the other lipids to fill in the gaps and hold them all together. It plays a similar role in our lipid nanoparticles. It provides structural support so the nanoparticles don't fall apart in between the injection and when they get into our cells. Third, there's a lipid called an ionizable lipid. Here, ionizable means that when these particles are in the bloodstream, they're neutrally charged, which helps with their safety. Then they switch to a positive charge inside of our cells, which helps them release the mRNA. Ionizable lipids are special because they have to be made in a lab, and scientists around the world have tested tens of thousands of these materials to find ones that are good at delivering mRNA safely. And because they're made in the lab, they tend to be proprietary to the company that invented them. So, for example, Moderna and BioNTech, the company that partnered with Pfizer, they discovered different ionizable lipids. And that is the only important ingredient in their COVID-19 vaccines that differ. And even then, their ionizable lipids aren't even that different, which is reassuring because when independent groups of scientists converge on similar solutions, it's easier to trust the result. Finally, one more ingredient. This one is a polymer called polyethylene glycol. So let's call it PEG. That's much easier. So PEG is a water-loving molecule. Okay? So it surrounds the lipid nanoparticle and it holds it all together. You can think of the other three lipids as the box and the bubble wrap for the mRNA, and the PEG as the packing tape. You may have heard in the news about a tiny fraction of people that have allergic responses to the vaccine. There is some evidence that PEG could be contributing to these allergic reactions. And that's because people are routinely exposed to PEG in cosmetic and household products, and some people have already developed antibodies against PEG. But why would this happen to some people and not to others? It turns out that every person's immune system is different, in just the same way that some people are allergic to latex, other people are allergic to PEG. It's important to keep in mind, however, that PEG has had a long history of safe use as part of FDA-approved drug formulations, and these vaccine allergies could be caused by things other than PEG. More research is needed to get to the bottom of these side effects. All right, so let's take a step back and look at our whole nanoparticle. When these ingredients all fit together nicely, the result is a delivery woman's dream. In the case of the vaccines, after these nanoparticles get injected into our muscle, they take the mRNA into our cells. There, the mRNA acts like an instruction manual that tells our cells to make a foreign protein, in this case, the coronavirus spike protein. When our immune cells see the spike protein, they rush to protect us from it, and they teach themselves to remember it so that they can kill it if it ever returns. As we speak, the mRNA vaccines are out there, saving lives from the coronavirus. They were our first and best tool to combat this nightmare, and they are our best hope of responding swiftly to viral variants because we can keep our lipid nanoparticle packaging the same, and all we have to do is swap out the mRNA that's inside. But here's the best part. For mRNA therapeutics, these vaccines are only the beginning. mRNA can be used to treat or cure many diseases. So, in the future, we will likely have treatments for many terrible diseases, including cystic fibrosis, muscular dystrophy, and sickle cell anemia. These diseases are caused by mutated proteins, and we can use mRNA to ask our cells to make the correct version of these proteins. We'll have treatments for cancer, breast, blood, lungs, you name it. We'll use mRNA to teach our immune cells how to find and kill cancer cells. And then, if we're lucky, we'll have vaccines against some of the most deadly and feared pathogens across the globe, including malaria, Ebola, and HIV. Some of these products are already in clinical trials, and the success of the COVID-19 vaccines will pave the way for future generations of these therapies. This is how the pandemic will save the lives of millions. It catalyzed the most rapid vaccine development in history and brought to life a niche, previously unapproved form of technology. And in our desperation, we gave that technology a chance. Now, we're collecting long-term safety and efficacy data from hundreds of millions of people. And with these data, interest in the technology, funding for the technology, and trust in the technology will continue to grow. Looking ahead, the packaging and delivery of mRNA to the right organs and tissues will continue to be one of the most significant challenges to implementing this technology. And so my colleagues and I are going to be busy for a very long time. Ultimately, I'm here with a message of hope. We are on the cusp of a revolution. mRNA is about to change the world forever, and it's all thanks to these fatty little balls that take this miracle medicine to exactly where it's needed. Thank you.
Since we're doing something a little different with this podcast, I wanted to do something different with our ads, too. I play a personal role in selecting sponsors for this podcast because they all help people navigate the changing landscape of work. Today, we're partnering with Hilton to answer questions about inclusive cultures and brave leadership. Consider this my version of office hours.
My dad is an architect, and he was really big into construction and whatnot. So I had this dollhouse that he built for me. And I told him, it's not a house, it's a hotel. When my mom looks back, it was like, you were meant for hospitality, even if you didn't know it.
Meet Macarena Moreno. She works on Hilton's operations team.
I just stumbled upon hospitality. I was like, this is for me. I love being around people. I love that customer-centric mindset. And I loved event planning at that point. So I was like, this is the career for me.
I recently joined Hilton for their 5th session of Courageous Conversations, a virtual learning series centered around a discussion on leading inclusively.
I love Hilton, and I was like, I'm so passionate about it. It's mostly the relationship you have with leaders. I've always been able to have such great conversations with senior leaders. They're always willing to listen and learn from you.
But in a culture built on hospitality, radical candor can sometimes be more challenging.
Being such a positive culture that we have within Hilton, sometimes it's just harder to have those conversations, right? Personally, I am a people pleaser. I know you describe yourself as a people pleaser as well. And just having tough conversations and just embracing conflict is complicated, right? It's something that I just don't do as much. And I think it's harder when your culture is so nice and so positive.
Maka was eager to discuss how to start that conversation with senior leaders. Although it's ultimately a leader's responsibility to open the door, we explored some ways for more junior people to walk through it.
With peers, I'm really great at creating that relationship. But once you start going higher up in the organization, I work with a lot of senior leaders at Hilton, it's harder to create that space, right? Do you wait for performance review? Do you say it like casually over coffee? Like, how do you bring that up?
The best thing I've seen in my working relationships is actually having a discussion about feedback as a norm. Maybe you set up a weekly meeting where you just dedicate 5 minutes of that meeting to say, okay, let's give each other feedback, or let's talk about what's going well in our work relationship and what's not. Have you had that conversation yet?
Well, I think I've had it with a couple of people. I don't think with my manager I've had that personal discussion, but I 100% agree. You have to create the space. It's hard because at least right now in hospitality, we've had like such a crisis mentality the past year. Now I think that things are calming down and focusing on recovery. You just need to find a time and space to really discuss that.
If hospitality is serving, which you clearly love to do, one way of serving people is to teach them. And I wonder if one of the ways that you can reframe some of these challenges of being radically candid as like opportunities for everyone to teach and learn. If we call it conflict, it sounds scary. If we say, hey, you know what, you should be teaching everyone you work with something, and you should be learning something from everyone you work with, maybe that makes it a little bit easier to get into.
I like that. I think that's going to be my next move.
Learn more about Hilton's award-winning culture and find a job you'll love at jobs.hilton.com.
TED Talks Daily is hosted by me, Elise Hu, and produced by TED. Theme music is from Allison Leighton Brown, and our mixer is Christopher Fazy Bogan. We record the talks at TED events we host or from TEDx events, which are organized independently by volunteers all over the world. And we'd love to hear from you. Leave us a review on Apple Podcasts or email us at podcasts@ted.com.
PRX.